All right. Hello, everyone. I am making this video since most of you are gone taking the PSAT. Hope that went well for you guys. We're just going to have you watch this at home or in class with headphones and fill in the notes on your own. This is the second part of 4.1. We're going to start by talking about multiplicity. And just a little intro to that. Let me focus this in. All right. Let's say you have a function such as f of x equals x squared plus 6x plus 9, okay? And if you wanted to solve that, of course, we know f of x is equal to y. So we'll put x squared plus 6x plus 9 equal to y. And then if you're solving, you're going to zero out that y because you're looking for where you cross, the x-axis. Solutions are roots, are x-intercepts, etc. All right, so this would factor into x plus 3 and x plus 3. And if you were solving, you would get x equals negative 3 and x equals negative 3. So you would get the same solution twice, which is what we call a double root, or a root of multiplicity 2. So when I'm talking about multiplicity, this is what I'm talking about, how many times a solution occurs. So let's get to the notes, and I can go a little faster now because you can always slow down and rewind. So multiplicity is the number of times the same number is a root. Again, that means a solution, a zero, an x-intercept, etc. So let's look at these three graphs here. So notice this is kind of like the one I just did. It's x minus 3 squared, whereas this one I could have written as x plus 3 quantity squared. So the one in the notes is very similar to the one I put on this post-it. Okay, so we're going to use our transformations to graph these. This is just going to be your parent parabola shifted right 3. So it's going to go through 3, 0. And then this y-intercept would end up being 9 when all was said and done. So, it looks something like this. The point is we see that it just touches the x-axis once. It has that double root, and it just touches down on the x-axis, so touches here. Or we can say tangent to the x-axis. All right, so x equal to 3 is what we call a double root. Or we say it has multiplicity of 2. All right, so this next one is our cubic, and that's going to be shifted right 3 also. And so it would look like this. And so please note this one actually crosses. All right, this is a cross. Crosses the x-axis. Okay, so we say x equal to 3 is a triple root. If you were to solve that out, this would be x minus 3, x minus 3, x minus 3, so that would be a triple root. Okay, so multiplicity of 3. And then the last one, this is x minus 3 to the 4th. So let's just take a sneak. You won't be able to see it. Let me get my TI. Hold on one second, guys. Try not to fall out of my chair. Okay, so if we were to graph this one, we would get x minus 3 quantity to the 4th and zoom 6 it. And so you see that we get this nice little parabolic shape. So it's to the 4th, but since it's so basic, it still kind of looks like a parabola. So it's a little thinner because it's got to have a y-intercept way up there at 81. All right, so this is 3, 0. The point is we see that x equal to 3 is a quadruple root, multiplicity of 4, and noticing that we just touch the x-axis. And so that's going to be a thing with even multiplicity. These two have even multiplicity, and they just touch the x-axis. This is odd multiplicity, and that actually crosses. So that's going to help us out when we go to analyze graphs. All right, so right here we get that c is a root of multiplicity 4. Or sorry, that's not a 4, that's a k. C is a root of multiplicity k. So you take the opposite here, so that would be positive c, and then this power is k, so c is a root of multiplicity k. All right, if root has odd multiplicity, it crosses. And if a root has even multiplicity, it just touches. Okay, so we're going to identify the real zeros here and talk about what their multiplicity. We're going to identify the real zeros and then talk about their multiplicity, and then write an equation whose leading coefficient is 1, so that makes it kind of easy. All right, so our real zeros here, we have x equal to -2, that's a cross. X equal to -1, that's a cross. X equal to 1, that's a cross. And x equal to 2, cross. One more, x equal to 3, cross. So all of these will have odd multiplicity because they're crossing. All right, so to write the most basic equation here, we would just write f of x equals, remember it said the leading coefficient is 1, so there's no a value here. And I'm just going to go in and, if you get a solution of x equal to -2, that came from x plus 2 in the parentheses. X plus 2, x plus 1, x minus 1. I'm going to jump down here just to save room. X minus 2 and x minus 3. Okay, and so this would be the equation that we see. This equation would be graphed right here. And you can pop that into your TI and verify it, but I'm just going to go ahead and move on to the next piece here so we don't get this video to be too long. All right, so here we've got x equal to -3 as a root, x equal to -2 as a root, x equal to 0 as a root, and x equal to 2 as a root. This one is odd. This one's odd multiplicity because it crosses. This one, however, is an even multiplicity because it touches. It does not cross the x-axis, it just hits it and then heads back down. And then x equal to 2 is odd, so it crosses. So the most simple equation I could write would be f of x equals, and let's start with the 0, okay? So when x equals to 0, that comes from x minus 0, right? Which is just x. So I'm going to start with that so it's in front. And that's got to be even, so that the first even number we have is 2. So I'm going to put x squared there, and then x plus 3, and odd, we'll just leave that at an exponent of 1, and x plus 2, and then x minus 2. That's the most basic polynomial that you could write. And again, you can check with your TI and see if indeed it looks something like this. They may have different a values. At some point, this might be an odd multiplicity of, instead of 1, it could have been, say, 3. But we're going to look at the max and mins and identify exactly kind of what degree each piece has. All right, so some observations that we have here. Number 1, a polynomial function of degree n has at most n zeros. Okay, so as we saw here, this was a square. So you're going to get 2 zeros. You're going to get 2 roots. And we got 2. Now, they may be the same thing, but it kind of just means you can account for both of them. You may have 2 different ones here. You may have 2 of the same, or you might have 2 imaginary. Or you might have 2, from the quadratic formula. But you can always account for 2 here. All right? And so a polynomial function of degree n has at most n zeros. And it really does have n zeros, just some of them may be triple, double, quadruple, or some may be imaginary. And then when you have turning points, it's going to be at most n minus 1. The turning points are always one less than the degree. So notice here I have a max and a min and a max and a min. So there are 4 turning points. I'm going to say 4 max mins. All right, so think about the degree here. The degree here would have been, if we were to multiply it all together, x, 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 and x, it would have been x to the 5th. Okay, and so that matches with a degree here, the max and mins, a degree of 5, we have 4 max and mins. And that is going to be a connection that we make. So same thing here, max, min, max, min. Okay, and this degree would have been x squared, x, x, and x, so that's 1, 2, 3, 4, 5. This would have been degree 5, and we see that we indeed get 4 max mins, 1 less than the degree. Another thing to note, both of these graphs have the behavior from what we learned yesterday. As x goes left, y is going down, and that's true for leading coefficient of odd, positive. And then as x goes to the right, y goes up. So you can see that consistency here, down to the left, up to the right, down to the left, up to the right, all matching with what we did yesterday. Okay, points of inflection. Remember, points of inflection are where concavity changes, where there's a change in concavity. So you're going to have n minus 2. If the degree's 5, you're going to have 3 of these. If you have a degree 5, you'll have 4 max-mins. Potentially, you may not have that many, but that's the most you can have. Degree 5, you won't have like 8, maxi-mins. And the most points of inflection you can have are, 2 less. So if it were 5, you would have 3. And so look at our POIs here. The concavity is beginning to switch here, and then here, and then it's concave up. These are all POIs. And notice we had 3. So that's consistent with what we just put in the notes. Point of inflection, point of inflection, point of inflection. 3 POIs here also. So 5, 4, 3. 3 POIs. All right. Let's look at the next page where we have some questions to answer, the type of questions you would see on a test or a quiz. All right. Analyze the polynomial function, identify all the key values, and sketch. Okay. Check with your TI. All right. So here is a polynomial function. Let's find the leading term. So the leading term here, the power function, would be, the leading term in the first factor is x. The next factor is x squared, and the last one would be x cubed. So we have a leading term of x, 6, x to the 6th power. So describe the end behavior there. So this is, positive and even. So we're going to have up in behavior. As x goes left, we are going to be up, and as x goes right, we're going to be going up. Okay, so 1, 2, 3, 4, 5, 6. That is even and positive lead. All right, identify and analyze the zeros. All right, so we would get x equal to 5. That would be a cross because it's odd multiplicity. That's a 1 right there. X equals 2 would be a touch because this is even. And x equal to negative 1 would be a cross. All right, because that is odd. Okay, so we're going to graph it, and what's the y-intercept? So let's go ahead and find the y-intercept first. F of x equals x minus 5, x minus 2, x minus 2, x plus 1, x plus 1, x plus 1. Okay, so if we were to plug in 0 for the y-intercept, let x equal to 0, you would just get negative 5 times negative 2 times negative 2 times 1 times 1 times 1. All right, so that is going to be negative 10, positive 10 times this is going to be negative 20. Uh-oh. It's dark here. Hold on. Okay, we're back. So y-intercept down here of negative 20. And I don't know if that's a max or a min. I don't know. But we're going to pass through that point. All right, we're going to cross at here at negative 1. And we're going to touch at 2. And then we're going to cross at 5. Okay, and then I've got to be going up. So I've just got to be going like this. And then I don't maybe make a turn here. Just touch it, and then up you go. So that's a potential graph. You can check with your TI. Again, I'm not going to do that, but you'll get, I don't know how low it goes here, and I don't know, it could have even gone low on this side. I don't know. Next year in calculus, that's what we'll find when we do our first derivative. But right now, you'd have to plot a point just to see where the max and min would be, but right now we're just doing it in general. Okay, next problem says construct a polynomial function with the given characteristics. Zeros, negative 4, multiplicity 1, 0, multiplicity 3, 2, multiplicity 1, degree 5, and contains this point. So now we don't have that the a value is 1. We don't have the leading coefficient is 1, so we're going to put an a there and solve for that. Let's start with 0 of multiplicity 3, because that's going to come from x minus 0 cubed, so I'm just going to write x cubed there to keep it simple. Negative 4, so that goes in at x plus 4 with multiplicity 1. 2, so x minus 2 of multiplicity 1. And it says we're at degree 5, so that makes sense because this would be 1, 2, 3, 4, 5. All right, so we're pretty good here, but we need to find the a value. So we're just going to use this x and this y here. And so remember, y is equal to f of x. So we'll just put 64 here, solve for a, negative 2 cubed, negative 2 plus 4, negative 2 minus 2, 64 equals a. That's negative 8 times 2 times negative 4, which happens to be 64a. So indeed, you know, a did come out to be, it's kind of a coincidence that we got a to equal to 1, but a would be equal to 1 here. And so you'll just put that into your equation, and you'll get f of x equals 1, which I'm not going to write, x cubed, x plus 4, x minus 2. Okay, so there's that. So again, this would be down to the left, up to the right. So we would be coming in on a cross, and a cross. Okay, so we'd have to do just something, I don't know, something like this. That's about all I can get out of that one. All right, so there's that problem. Let me look at the notes here, see what happened on that one. Yeah, so same thing, just something like that. So even though it was degree 5, it only had 2 max and mins, and that's fine. It can just have as most, it can have as most 4 terms. This one happened to only have 2, and that's okay. That's what it looks like. All right, last one. The following is a complete graph of a polynomial function. Is the degree even or odd? Okay, so this goes same direction, down, down. So we know this had to be even. Okay, is the leading coefficient positive or negative? And that's going to be negative. Well, we shouldn't say it's even because it's down, down. We should say it's even because it's same direction. And then we can say it's negative because it's down, down. All right, here we go with the zeros again. Negative 2, that's a touch. X equal to 0, that's a cross. X equal to 2, that's a cross. Okay, so determine the smallest possible degree of him. So we have 3 zeros. All right, but this one must have an even multiplicity. All right, so how many zeros? 3. 1 is a double root. So, you know, the most simple, we'll just let a be 1. The most simple thing I could do is say that x plus 2 is squared, and then x is odd. We'll just leave that at you know, x minus 0, since it's there. I'll just do that, and we'll leave that. All right. So even, odd, odd, touch, cross, cross. So this would be degree. That would be the smallest degree I could find, degree 4. But I want to check to see if I'm right by looking at the turning points. So turning points, 1, 2, 3, 4, 5. There are 5 turning points. So that's going to have to come from at least a degree 6. It might come from a degree 7, 8, but it said to find the smallest. So now I'm thinking degree 6 here. And let's just check the POIs, changes in concavity, 1, 2, 3, 4. And so 4 POIs, and that's got to be 2 less than the number. So what's the smallest possible degree? Well, turning points, we could just use this. Turning point is the degree minus 1. We have 5 turning points. So this indeed is a 6th degree polynomial. So what I would need to, so degree 4 did not work, we need degree 6. So I'm going to rewrite this real quick with my erasable pen and show you our options. So we have x, x plus 2, and x minus 2. And this one right here, we need to have, you know, even. So we got to build this to 6. So maybe we're 3, 2, and 1. So maybe this is 3, 2, and this is 1. That means 1, 2, 3, 4, 5, 6. Or maybe this is just 1, and this is 3. That's another option if you were trying to write one. So that's 1, 2, 3, 4, 5, 6. Or maybe these are both 1, and this one jumps to 4. I don't know. You could try them and see which one matches this graph. But this is a good test question. And you just can't say, oh, there's 3 zeros, 1's a double root, boom, the degree's 4. You have to really think about the turning points and the points of inflection as well. All right, that is it for 4.1. Hope you understood and got your notes filled out, and I will look forward to seeing everyone next class period to start 4.2. All right, bye now.